Imagine floating silently through the vastness of space, where gravity's gentle pull guides you past glowing planets and mysterious moons. There is no hurry here, only the quiet hum of the cosmos and the soft light of distant stars. Before we begin this serene journey through our solar system, take a moment to settle in, breathe, and prepare to drift along with us. As you follow, you will learn the unique stories of each planet, their moons, and the subtle rhythms that govern their orbits. Keep listening to uncover the hidden wonders of our celestial neighborhood, from the blazing sun to the smallest icy moons, and allow your curiosity to float freely across the stars.
Drifting gently outward from the quiet familiarity of Earth's orbit, imagine yourself moving into the silent expanse of space. A vast darkness stretches endlessly, yet even here there is rhythm, subtle currents of gravity and motion guiding every particle and world. The solar system reveals itself not in haste, but in patient, unfolding layers of light, mass, and energy. At its center, a glowing sphere anchors the entire celestial dance, radiating warmth and light across billions of kilometers, shaping orbits, climates, and atmospheres. Keep listening to discover the wonders of the Sun and Mercury, the first companions in this gentle journey through our solar neighborhood. The Sun dominates the inner system, an enormous sphere of incandescent plasma, primarily hydrogen and helium, engaged in perpetual nuclear fusion. Each fusion reaction converts mass into energy, sending sunlight and solar wind outward in all directions. Its surface is a boiling mosaic of granules, convection cells rising and falling in quiet, rhythmic patterns. Sunspots appear as darker, cooler regions, temporary features that hint at magnetic activity churning beneath the visible surface. Occasionally, prominences and solar flares arc into space, delicate filaments of charged plasma twisting under magnetic influence, casting gentle energy across the inner planets. From this distance, one senses not only the immense power, but also the subtle order maintained by gravity and fusion, a rhythm that has endured for billions of years. Above the surface, the corona extends outward, a tenuous halo of charged particles stretching millions of kilometers into space. It glows faintly in ultraviolet and X-ray light, invisible to the naked eye, yet influencing every planet through solar wind. These particles interact with planetary magnetic fields and atmospheres, sculpting auroras, charging upper atmospheres, and shaping the very space between worlds. Floating in this quiet region, one can appreciate how the sun governs the motions of planets, the chemistry of atmospheres, and the delicate balance of energy that sustains life on the third planet from its warmth. The first planet encountered in this inner journey is Mercury, the closest to the sun. Small, dense, and rocky, it presents a surface sculpted by impacts, contraction, and ancient volcanism. Its proximity to the sun exposes it to intense radiation, producing surface temperatures that soar to over 400 degrees Celsius during the day and plunge below minus 180 degrees Celsius at night. Mercury rotates slowly, completing a single spin in about 59 Earth days, while orbiting the Sun in 88 days, resulting in unique day-night cycles that bathe its plains in prolonged light or shadow. From above, the planet appears as a cratered, mottled orb, a testament to billions of years of cosmic collisions. Impact craters dominate Mercury's landscape, varying in size from tiny pits to massive basins hundreds of kilometers across. The Caloris Basin, one of the largest impact structures in the solar system, stretches over 1,000 kilometers, its rim and interior revealing fault lines and concentric rings shaped by immense pressure and heat during formation. Across the plains, smaller craters pepper the surface, each a record of collisions with meteoroids and comets over eons. Smooth plains between craters indicate ancient lava flows, evidence of volcanic activity that reshaped the terrain long after the early bombardment. Scarps, or cliffs, snake across the landscape, raised edges of crustal contraction that hint at the planet cooling from an initially molten state. These features, when observed from above, create a tapestry of history where time is measured in eons rather than days. Mercury's exosphere is exceedingly thin, composed of trace amounts of helium, sodium, potassium, and hydrogen, almost non-existent compared to the denser atmospheres of its neighbors. Solar wind strikes the surface directly, dislodging atoms into space and creating a faint, ethereal halo around the planet. Though fragile and sparse, this exosphere interacts with the sun's magnetic field, producing subtle emissions and revealing the continuous silent interplay between solar energy and planetary material. These delicate processes are invisible to the human eye, but critical to understanding Mercury's environmental dynamics. The planet's rotation and orbital motion combine to create unusual observational phenomena. Because Mercury's day is longer than its year, one side basks under the sun's gaze for weeks, while the other endures prolonged darkness and cold. Temperatures swing dramatically, emphasizing the importance of even a thin atmosphere in regulating heat. Shadowed craters near the poles, shielded from sunlight, retain deposits of water ice, quietly preserved for potentially billions of years despite the proximity to the sun. These ice-filled craters are among the few places in the inner solar system where cold and darkness combine to preserve ancient matter, subtle relics in an otherwise harsh environment. Mercury's internal structure contributes to its character. It has an unusually large metallic core, making up about 75% of the planet's radius, surrounded by a thin silicate mantle and crust. This dense core generates a weak but detectable magnetic field, a faint echo of the dynamo processes that occur in larger planets like Earth. The magnetic field interacts with the solar wind, creating magnetospheric currents that ripple subtly through the surrounding space, guiding charged particles and influencing the exosphere. These quiet, invisible forces are as essential to Mercury's identity as its craters or plains, shaping conditions over geological time. Exploring the planet from orbit, one notices the interplay of light and surface material. Sunlight reflects differently from cratered highlands versus smooth lava plains. Shadows cast by crater rims highlight relief, revealing depth and subtle textures across the terrain. Dark hollows, shallow depressions often near crater floors, may result from volatile elements escaping the surface, leaving pits that catch the eye. Such delicate details reveal the complexity of a seemingly simple world, where even small features tell stories of planetary evolution and cosmic interaction. Mercury's temperature extremes influence chemical reactions and surface processes. Daytime heat drives expansion and contraction of surface rock, producing stress fractures that slowly reshape terrain. Nighttime cold contracts rock, occasionally triggering small quakes or shifts in crustal layers. These cycles, imperceptible in human terms, cumulatively sculpt landscapes over millions of years. The planet's arid, exposed surface preserves these subtle changes, allowing us to read its geological history as a long, quiet narrative. The inner solar system's proximity to the sun creates unique illumination patterns. Mercury's surface reflects minimal light, a muted gray punctuated by bright crater walls. The sun, large and intense in the Mercurian sky, casts sharp shadows that highlight the textures and contours of the rocky terrain. Observing these effects emphasizes the importance of light, angle, and reflection in shaping planetary perception, teaching that even barren landscapes have stories to tell when viewed with attention and patience. Volcanic plains provide further insight into Mercury's evolution. Ancient lava flows, now solidified and heavily cratered, reveal a period when the planet's interior remained hot enough to drive surface activity. The patterns of these flows, interspersed with impact features, create a layered history of energetic events, showing that Mercury is not a static relic, but a world that has continuously interacted with its environment, even in subtle, quiet ways. Mercury's craters are more than scars, they are time capsules. Some preserve evidence of impact melt, the temporary flow of molten rock during collisions. Others contain central peaks formed by the rebound of the surface after an impact. Patterns of secondary craters, ejectolays, and overlapping formations document sequences of events, providing a chronological record of celestial collisions. This history, etched in stone and dust, speaks to the persistent energy of the solar system and the enduring influence of gravity and motion. The poles of Mercury are particularly intriguing. Permanently shadowed regions within craters harbor water ice, a remarkable anomaly on a planet so close to the Sun. This ice exists in thermal equilibrium with extreme cold and sparse exposure to sunlight, preserved for eons in a quiet, isolated state. Its presence hints at delivery by comets and asteroids over time, subtly linking Mercury to the broader solar system. Observing these areas, one senses the hidden complexity of even the smallest planet, the interplay of sunlight, shadow, and cosmic history creating unique environments. Mercury's interaction with the Sun extends beyond heat and light. The solar wind constantly bombards the surface, knocking atoms into the exosphere, while energetic particles create subtle electrical currents in the crust. This continuous, silent interaction illustrates that no planet exists in isolation. Each is part of an extended system governed by energy, mass, and motion. Mercury's apparent stillness masks a dynamic interplay of forces, a quiet testimony to the complexity of planetary systems. Even the planet's orbital eccentricity affects its character. Mercury's slightly elongated orbit means its distance from the Sun varies significantly, influencing temperature, illumination, and solar gravitational effects. Perihelion brings the planet closer to the Sun, exposing surfaces to intense radiation, while aphelion moves it farther away, allowing temporary relief from heat. This constant variation, subtle yet persistent, shapes the planet's environment in a predictable rhythm, a quiet heartbeat dictated by orbital mechanics. Looking down upon the planet from above, one notices textures, gradients, and contrasts in sunlight and shadow. High-resolution mapping reveals scarps twisting across planes, crater chains marking impact sequences, and smooth plains punctuated by isolated peaks. The variation in albedo across regions hints at compositional differences and historical processes, telling a story in stone, dust, and ice. Observing these details instills appreciation for the patience required to understand planetary evolution, where each feature is a clue to ancient events.
Continuing outward from Mercury, the journey drifts toward Venus, a world shrouded in dense, swirling clouds that obscure the surface from view. From orbit, the thick, golden haze glows under the sun's rays, reflecting and scattering light in a soft, perpetual shimmer. Venus rotates slowly, taking 243 Earth days to complete a single turn, and spins in a retrograde motion, causing the sun to rise in the west and set in the east. Beneath its thick carbon dioxide atmosphere, the surface experiences extreme pressures and heat, creating an environment both hostile and mesmerizing. From above, the planet appears alive with motion, not of water or vegetation, but of winds racing around the globe at hundreds of kilometers per hour, circling the planet faster than its rotation, sculpting the cloud patterns in constant, silent dance. The surface of Venus, revealed only through radar mapping, tells a story of volcanic renewal and tectonic activity. Vast plains of solidified lava stretch across the equatorial regions, interspersed with rugged highlands and rift valleys. Volcanoes rise quietly from the terrain, some dormant, others possibly still active, hinting at an inner heat that continues to shape the planet. Shield volcanoes, broad and gently sloping, dominate the landscape, evidence of slow lava flows over millions of years. Craters exist, but fewer than on Mercury, their scarcity a testament to Venus's capacity to renew its surface, erasing ancient scars under a veil of molten rock. Sulfuric acid clouds drift ceaselessly in Venus's upper atmosphere, catching sunlight and scattering it into muted rainbows of reflective haze. Lightning occasionally arcs within these clouds, though the precise mechanisms remain mysterious, adding subtle flashes of energy to an otherwise constant, softly flowing sky. Beneath this dynamic layer,
The surface is locked in a greenhouse grip where temperatures soar above 460 degrees Celsius, hot enough to melt lead. Winds sculpt the cloud decks, producing streaks and swirls that trace invisible currents of energy and heat, revealing the intimate connection between atmosphere and solar influence. Moving outward, Earth presents a dramatic contrast to its neighboring world. Blue oceans shimmer under sunlight, interspersed with continents displaying mountains, deserts, forests, and ice caps. Clouds drift gracefully across the surface, reflecting sunlight and shaping weather systems in gentle, ongoing patterns. Earth's atmosphere, rich with nitrogen and oxygen, supports life and regulates climate, producing a balance between warmth, precipitation, and air circulation. From above, the rotation of Earth is a comforting, predictable rhythm, a constant heartbeat in the solar system that governs day and night, influences tides, and shapes the climate in subtle, interconnected ways. Oceans cover the majority of Earth's surface, their currents circulating warmth from equator to poles, regulating temperature and sustaining marine ecosystems. Mountain ranges rise, shaped by tectonic collisions and volcanic activity over millions of years, creating barriers that influence weather and precipitation. Deserts expand and contract with seasonal variations, while forests change color and density with the cycles of life. Polar ice reflects sunlight, creating shifting mosaics of white that interact with ocean currents and atmospheric patterns. Observing Earth from orbit, one appreciates not only its beauty, but its intricate systems, a delicate interplay of water, air, land, and life maintained over eons. Life on Earth adds another layer of fascination. The planet's biosphere contributes to chemical cycles, atmospheric composition, and energy flows in subtle yet profound ways. Photosynthesis converts sunlight into chemical energy, sustaining plants and the creatures that depend on them. Respiration, decay, and nutrient cycling form closed loops that maintain balance, while migration, reproduction, and adaptation demonstrate life's dynamic response to environmental change. From above, these processes are invisible, yet their cumulative effect shapes the planet's appearance and the conditions experienced on the surface. Mars, the red planet, appears as a quiet, rust-colored orb at the edge of the inner solar system. Its surface is covered with iron oxide dust, giving it a distinctive hue, while vast plains, ancient riverbeds, and impact craters tell the story of a dynamic past. Mars rotates at a pace similar to Earth, approximately 24.6 hours per day, and is tilted at 25 degrees, producing seasons that shift polar ice and influence atmospheric circulation. Although its thin atmosphere cannot retain heat, dust storms sweep across plains and valleys, creating transient shifting patterns that sculpt the landscape. The polar caps, composed of water and carbon dioxide ice, grow and recede with seasonal changes, reflecting sunlight and subtly modifying the planet's climate.
Olympus Mons, the largest volcano in the solar system, rises from the Martian plains in quiet grandeur. Its slopes, layered with lava flows, record the planet's geological activity over millions of years. Valles Marineris, a canyon system stretching thousands of kilometers, carves deeply into the crust, revealing fractures, sediment layers, and evidence of past erosion. Smaller volcanoes, impact craters, and dust dunes add texture and depth, each feature a marker of time and energy. Even minor dust devils, spiraling across plains, subtly reshape the surface, demonstrating that change occurs even in a seemingly static environment. Mars's atmosphere, mostly carbon dioxide with traces of nitrogen and argon, is thin but dynamic. Winds circulate dust, influence temperature, and interact with seasonal ice caps. Despite its tenuous nature, the atmosphere plays a role in transporting heat, shaping weather patterns, and facilitating surface processes. During dust storms, fine particles scatter sunlight, producing soft, diffuse illumination that casts an eerie, muted glow across the landscape. These subtle atmospheric effects
highlight the delicate interplay between thin air, solar radiation, and planetary rotation. Craters and valleys record the history of impacts, water flow, and tectonics. Ancient riverbeds, deltas, and lake basins indicate a wetter past, suggesting that liquid water once shaped the Martian surface. These features, preserved over billions of years, provide insight into past climates and potential habitability. Ice in craters and beneath the surface preserves traces of ancient water, quietly linking the present to a distant dynamic history. Mars's surface, scarred yet beautiful, offers a window into the processes that have sculpted terrestrial planets across time. Temperature extremes define the Martian environment. Daytime highs reach comfortable warmth in equatorial regions, while nighttime lows plunge far below freezing. Seasonal changes and dust storms further modulate temperatures, producing a constantly evolving yet subtle environment. These cycles influence surface chemistry, erosion rates, and potential habitats for past or present microbial life. Even in its apparent barrenness, Mars is a planet of quiet complexity, shaped by forces both visible and hidden. Magnetic anomalies remain from an earlier era, localized regions of crustal magnetization that provide faint protection from solar wind. While the planet no longer has a global magnetic field like Earth, these remnants influence particle movement, auroral phenomena, and atmospheric retention. Mercury, Venus, Earth, and Mars each illustrate a unique approach to magnetism, rotation, and atmosphere, revealing the diversity of planetary evolution under a single solar influence. Observing Venus, Earth, and Mars together, one perceives a spectrum of planetary character. Venus embodies heat, pressure, and motion. Earth balances warmth, water, and life. Mars preserves history, subtle weather, and geological record. Each world contributes to an understanding of how proximity to the Sun, atmospheric composition, rotation, and internal structure define the environment. The contrasts are instructive, the details endless, yet all exist within a harmonious system governed by solar gravity, orbital mechanics, and the passage of time. The dance of light, shadow, and surface composition continues across these worlds. Sunlight illuminates features, revealing contours, textures, and chemical contrasts. Shadows lengthen across plains and valleys, highlighting depth and form. Reflected light from clouds, ice, and oceans creates subtle gradients, a palette that changes with time, season, and perspective. These interactions offer a visual meditation, emphasizing that observation, patience, and attention reveal the profound stories of planetary evolution. Volcanic activity, erosion, ice cycles, and wind patterns demonstrate that change is constant yet gradual. Venus's cloud movements, Earth's oceans and tectonics, Mars's dust storms and ice cap shifts all contribute to planetary narratives unfolding over millions of years. In these subtle movements, one sees the interconnectedness of energy, matter, and motion. The planets, though silent and distant, teach with presence, offering lessons in time, resilience, and the quiet shaping forces of the cosmos. The inner solar system, from Mercury through Mars, presents a tapestry of extremes and balance, heat and cold, pressure and scarcity, abundance and limitation. Each planet is an individual expression of physical laws, a unique response to solar radiation, mass, composition, and orbital dynamics. Observing them calmly, without haste, encourages an appreciation for diversity,
the subtle interactions of energy and matter, and the patient unfolding of cosmic history. From the scorched plains of Venus to Earth's dynamic surface and the red, quiet deserts of Mars, the inner planets form a foundation for understanding the solar system. They reveal the interplay of formation processes, internal structure, and solar influence, preparing the observer for journeys outward, toward asteroids, dwarf planets, and beyond, where the scale, composition, and complexity of celestial bodies expand further.
Drifting outward from the inner planets, a subtle shift occurs as the sun's gravitational grip extends its influence across the vast expanse between Mars and Jupiter. Here, a region of scattered rocky bodies emerges, the asteroid belt, a quiet archive of the early solar system. It is neither planet nor empty void, but a collection of fragments, each with its own shape, size, and history. Floating among these objects, one senses the silent passage of time, the remnants of formation processes that never coalesced into a larger world, and the gentle rhythm of motion maintained by gravity and orbital mechanics. The asteroid belt contains millions of bodies, ranging from dust-sized particles to Ceres, the largest object within the belt. Though small compared to planets, each asteroid preserves clues about the materials present in the early solar system. The diversity is striking. Some are composed largely of rock and metal. Others are rich in carbon compounds, water ice, and volatile minerals. Studying these fragments provides insight into the building blocks that contributed to planetary formation, a mosaic of primordial matter frozen in a cosmic snapshot. Ceres, the belt's largest member, measures approximately 940 kilometers in diameter. Its surface is marked by impact craters, subtle variations in brightness, and evidence of water ice near the poles. Bright spots within certain craters, composed primarily of salts, reflect sunlight and hint at past or even ongoing interactions between subsurface brines and the surface. These details suggest a planetesimal that has undergone differentiation, with a core, mantle, and crust, albeit on a much smaller scale than the inner planets. From orbit, the surface appears pockmarked but nuanced, a record of billions of years of collisions, thermal evolution, and surface modification. Vesta, the second largest asteroid, offers another perspective. Its basaltic surface, shaped by ancient volcanism, hints at a differentiated interior. Large impact craters expose layers of rock, allowing us to peer into its geological history. Vesta's rotational period is relatively fast, completing a spin in just over 5 hours, giving it a slightly oblate shape due to centrifugal forces. From afar, the variation in albedo across its surface paints a complex picture of impact scars, ridges, and older volcanic regions. Observing Vesta reminds one that even smaller bodies carry intricate histories, silent witnesses to the formative events of the solar system. Asteroids vary widely in composition. Carbonaceous asteroids contain organic molecules and water-rich minerals, remnants of the primordial nebula that formed the Sun and planets. Silicate-rich asteroids, primarily composed of rocky minerals, record the thermal and collisional processes that shaped their interiors. Metallic asteroids, rich in nickel and iron, may represent the cores of larger disrupted bodies. Each type serves as a cosmic archive, a preserved record of materials and conditions present billions of years ago. The orbital dynamics of the belt are subtle yet profound. Asteroids follow elliptical paths around the Sun, their motions influenced by the gravitational tugs of Jupiter and Mars. Gaps in the distribution, known as Kirkwood gaps, reveal regions where resonances with Jupiter's orbit have cleared material over time. Collisions among asteroids are rare on human timescales, but inevitable over millions of years, creating debris, altering orbits, and contributing to the ever-changing structure of the belt. Observing these motions, one senses a quiet balance, a celestial dance where chaos and order coexist over eons. Smaller bodies in the belt, some only meters across, drift like cosmic grains of sand. Their surface is weathered by micrometeorite impacts and solar radiation.
Over time, collisions produce fragments that may coalesce temporarily before being shattered again, a continuous cycle of destruction and renewal. These processes are imperceptible in the moment, but collectively sculpt the belt structure, reminding observers that change is constant, even in regions that appear still and desolate. Asteroids occasionally produce meteoroids that escape the belt and enter the inner solar system. Some of these collide with Earth, delivering minerals, organics, and even water to the surface. Meteorites that reach Earth's surface offer direct study opportunities, allowing scientists to analyze the composition of these ancient bodies. Each fragment carries stories of formation, impact, and survival, tiny time capsules connecting our planet to the wider solar system. The interplay between sunlight and asteroid surfaces produces subtle illumination effects. Shadows cast by irregular shapes reveal contours, ridges, and depressions, while reflective surfaces capture glints of light. The contrast between dark carbonaceous bodies and brighter silicate or metallic ones creates a visual mosaic that changes with viewing angle and solar position. Observing these variations provides insight into surface composition, texture, and age, a slow, meditative study of celestial diversity. Temperature variations across the belt are dramatic despite its distance from the sun. Daytime surfaces exposed to sunlight may warm to hundreds of Kelvin, while shaded regions plummet near absolute zero. These fluctuations drive thermal stresses, leading to cracking, regolith formation, and subtle reshaping of surfaces over long periods. Even absent atmospheres, the effects of temperature cycles contribute to the continuous evolution of these small worlds. Asteroids occasionally produce meteoroids that escape the belt and enter the inner solar system. Some of these collide with Earth, delivering minerals, organics, and even water to the surface. Meteorites that reach Earth's surface offer direct study opportunities, allowing scientists to analyze the composition of these ancient bodies. Each fragment carries stories of formation, impact, and survival, tiny time capsules connecting our planet to the wider solar system. The interplay between sunlight and asteroid surfaces produces subtle illumination effects. Shadows cast by irregular shapes reveal contours, ridges, and depressions, while reflective surfaces capture glints of light. The contrast between dark carbonaceous bodies and brighter silicate or metallic ones creates a visual mosaic that changes with viewing angle and solar position. Observing these variations provides insight into surface composition, texture, and age, a slow, meditative study of celestial diversity. Temperature variations across the belt are dramatic despite its distance from the sun. Daytime surfaces exposed to sunlight may warm to hundreds of Kelvin, while shaded regions plummet near absolute zero. These fluctuations drive thermal stresses, leading to cracking, regolith formation, and subtle reshaping of surfaces over long periods. Even absent atmospheres, the effects of temperature cycles contribute to the continuous evolution of these small worlds.
The asteroid belt is more than a collection of rocks. It is a record of early solar system processes. Gravitational interactions prevented coalescence into a planet, while collisions and fragmentation created diversity. Some asteroids are primordial, preserving their original composition, while others are fragments of larger bodies that experience differentiation and disruption. Together, they form a tapestry of history, a bridge between the inner planets and the massive gas giants beyond. Observing asteroids from above, one appreciates their distribution and density. Regions with higher concentrations of bodies contrast with sparser zones, revealing patterns shaped by gravitational influences. The belt is not uniform. Clusters, gaps, and families of asteroids trace back to collisional events and orbital resonances. Even subtle forces like the Yarkovsky effect, thermal radiation altering orbits over millions of years, play a role in slowly redistributing material. These gentle, persistent processes illustrate the dynamic yet balanced nature of the belt. Asteroid families offer further insight into solar system history. When a large body undergoes a catastrophic impact, fragments share similar orbital characteristics, creating a family that can be traced back to the original parent. Studying these families provides a window into collisional mechanics, material properties, and the evolution of the belt over billions of years. From orbit, one observes subtle clustering patterns, gentle reminders of violent events long past. Ceres and Vesta are merely the largest members of a vast population. Thousands of smaller asteroids, each with unique shapes and surface features, drift in silent orbits. Some are irregular, like elongated potatoes, while others approach spherical symmetry. Craters, ridges, grooves, and scars mark each surface, recording histories of collisions and thermal evolution. From a distance, the belt appears as a dispersed cloud of bodies, yet each fragment contains a wealth of information about early solar system processes. The asteroid belt's interaction with nearby planets is subtle but significant. Jupiter's massive gravity shapes resonances, clearing certain orbital zones and shepherding asteroids into stable orbits. Mars exerts smaller perturbations, influencing near-edge asteroids and contributing to the slow migration of some bodies inward or outward. This interplay highlights the interconnectedness of the solar system, where even small bodies respond to the gravitational presence of distant giants. Within the belt, some bodies exhibit unusual characteristics. Metallic asteroids, possibly remnants of planetary cores, reveal dense reflective surfaces. Carbon-rich asteroids carry organic compounds and water-altered minerals preserved from the solar system's earliest epochs. Others, mixtures of rock and ice, hint at processes that occurred in colder regions and were later perturbed inward. Observing these objects illuminates the diversity of formation environments, a spectrum of conditions captured in small, silent worlds. Dust and debris circulate throughout the belt, produced by collisions and surface erosion. Micrometeorites, vaporized by impacts or solar radiation, contribute to a diffuse cloud of particles. This dust interacts with sunlight, creating faint scattering effects visible in sensitive observations. Though imperceptible in real time, these subtle phenomena underscore the persistent influence of even tiny components, shaping the environment and slowly modifying surfaces. Occasionally, larger fragments are perturbed by gravitational interactions or collisions, becoming near-Earth objects that traverse orbits intersecting our planet. Their journeys provide tangible connections between the distant belt and our own world, reminding us that no region of space is truly isolated. These wandering bodies carry material from primordial sources, linking Earth to the broader history of the solar system. The asteroid belt is a living record, not in the sense of life, but in the continuous interaction of matter, energy, and time. Each body evolves through impacts, thermal cycles, radiation exposure, and gravitational forces. Observing these processes from orbit reveals the cumulative effect of quiet change over billions of years, a narrative written in stone, ice, and metal. Beyond individual bodies, the belt's overall structure reveals the imprint of solar system evolution. Clustering of asteroids, distribution gaps, and orbital resonances with Jupiter reflect the long-term effects of planetary formation, migration, and gravitational sculpting. From a serene vantage, one perceives order emerging from apparent randomness, the silent hand of physics shaping the architecture of this region. Temperature, radiation, and collisions collectively define surface properties. Regolith forms as rocks fracture and erode. Impact melts create temporary flows, and radiation darkens surfaces over time. These processes are gradual, continuous, and persistent, shaping landscapes imperceptibly yet profoundly. Even in the emptiness of space, the belt demonstrates the quiet passage of geological and cosmic time. Patterns of rotation among asteroids vary. Some rotate rapidly, their centrifugal forces affecting shape and surface features. Others tumble slowly, their axes chaotic due to past collisions. These motions influence regolith distribution, slope stability, and surface exposure to sunlight, subtly modifying environmental conditions. Observing these behaviors emphasizes the diversity of small bodies and the gentle mechanics governing their evolution. In totality, the asteroid belt forms a bridge between the inner rocky planets and the gas giants beyond. It is a repository of ancient material, a record of early processes, and a laboratory for understanding planetary formation and evolution. Floating quietly among these bodies, one experiences the slow, persistent pulse of the solar system, where even small fragments play a part in the broader cosmic narrative.
Beyond the crowded expanse of the asteroid belt, the solar system opens into a quieter realm where smaller worlds inhabit stable orbits and reveal the diversity of planetary formation. Among these, dwarf planets emerge as significant yet understated members. They are not planets by traditional classification, yet their mass, shape, and orbital dynamics distinguish them from ordinary asteroids. In this serene region, one can appreciate how the solar system accommodates a spectrum of bodies, from rocky inner planets to icy or metallic small worlds, each contributing to the architecture of the system. Ceres, residing within the asteroid belt, is the largest of these intermediate worlds. Its nearly spherical shape and differentiated interior reveal a complex history. Beneath a surface marked by craters and bright salt deposits lies a potential subsurface ocean, slowly preserved beneath layers of rock and ice. Observing Ceres from orbit, the surface features a subtle interplay of light and shadow across its craters, ridges, and plains. The bright spots within Akator crater reflect sunlight, hinting at past or ongoing interactions with liquid brines below. Ceres serves as a reminder that even seemingly small worlds may harbor intricate processes and histories comparable to much larger planets. Moving outward, Pluto resides in the distant Kuiper Belt, an icy, sparsely populated region beyond Neptune. Pluto's orbit is eccentric, tilted, and elongated, taking it closer and farther from the Sun in a 248-year cycle. Its surface is a patchwork of nitrogen, methane, and carbon monoxide ices, with regions of bright plains and dark, rugged terrains. Tumbal Regio, the heart-shaped nitrogen ice plain, reflects sunlight and reveals convection patterns, a sign of slow, persistent resurfacing. Mountains of water ice rise above these plains, their sharp peaks contrasting with the smooth, icy expanses, evidence of internal geologic activity. Pluto's 5 moons, particularly Charon, create a binary system that exemplifies gravitational interaction. Charon, nearly half the size of Pluto, shares a synchronous orbit with the dwarf planet, presenting a constant face to its companion. Their mutual gravitational influence shapes both rotation and orbital stability, while tidal forces may drive internal heating, subtly affecting geologic activity. Observing this system demonstrates the complex interdependence of bodies in the outer solar system, even at great distances from the Sun's warmth. Haumea, another distant dwarf planet, presents a unique form and rotational dynamic. Rapidly spinning, it has an elongated, ellipsoid shape unlike the near-spherical forms of other dwarf planets. Its surface is composed largely of water ice, and observations suggest collisional history and potential moons, each orbiting in patterns dictated by gravitational equilibrium. The rapid rotation, combined with surface composition, creates variations in reflected light, producing observable brightness fluctuations over its rotation period. Haumea exemplifies how diversity in mass, spin, and composition generates unique planetary characteristics. Makemake, located in the Kuiper Belt as well, is slightly smaller than Pluto and exhibits a bright, icy surface. Methane ice dominates its landscape, reflecting sunlight and creating a persistent glow from a distance. Its rotation is relatively slow, and though it may host small moons, their presence remains subtle, contributing minimally to the dwarf planet's overall dynamics. Makemake orbit, moderately inclined and elongated, emphasizes the diversity of paths these distant worlds follow, each shaped by ancient interactions with Neptune and neighboring Kuiper Belt objects. Eris, the most massive known dwarf planet beyond Pluto, resides in the scattered disk, a region of highly eccentric orbits influenced by Neptune's gravity. Its surface is composed largely of frozen methane, reflecting sunlight in a muted, steady glow. Eris's orbit takes it far beyond the traditional Kuiper Belt, highlighting the expansive and varied nature of the solar system's outermost regions. Its moon, Dysnomia, orbits closely, providing additional insight into mass, density, and orbital mechanics. Studying Eris demonstrates how gravitational perturbations, collisions, and resonance contribute to shaping the orbits and characteristics of distant objects. Each dwarf planet reflects a balance between self-gravity, solar influence, and collisional history. Unlike small asteroids, they are massive enough to assume near-spherical shapes, a sign that gravity has sculpted them into equilibrium forms. Yet their compositions remain diverse, from rocky and metallic to icy and volatile-rich. These characteristics preserve conditions from the early solar system, acting as time capsules that record the distribution of elements, thermal evolution, and the outcome of early collisions. Observing these distant worlds requires patience and sensitivity. Their surfaces are faint, illuminated weakly by sunlight, and often obscured by distance, orbital inclination, and reflective properties. Yet each observation, whether via spacecraft or telescope, reveals subtle surface variations, atmospheric traces, or interaction with nearby moons. From afar, these signals tell stories of impact events, internal processes, seasonal changes, and chemical composition, connecting the distant reaches of the solar system with the inner planets explored earlier.
The Kuiper Belt, where many of these dwarf planets reside, is itself a dynamic environment. Icy bodies orbit the Sun at great distances, influenced by Neptune's gravity and occasional collisions among themselves. The belt contains a vast population of objects, some small, some approaching planetary size, each moving in quiet, predictable paths that trace the architecture of the solar system's formation. Over billions of years, gravitational perturbations and orbital resonances have sculpted this region, leaving a structured yet varied collection of bodies. Beyond the Kuiper Belt, scattered disk objects and detached bodies extend the diversity of small worlds. Orbits become highly eccentric and inclined, shaped by interactions with Neptune and perhaps even distant, unseen masses. These regions preserve a record of the early gravitational sculpting of the solar system, containing objects that escaped incorporation into planets and maintaining chemical signatures from primordial times. In observing them, one perceives the vastness and complexity of the outer solar system, a realm where time and distance dominate the pace of change. Each dwarf planet contributes uniquely to understanding solar system evolution. Ceres preserves conditions from the inner belt, while Pluto, Haumea, Makemake, and Eris reveal the chemistry, dynamics, and structure of the outer system. Their surfaces, orbits, and moons provide laboratories for studying gravity, composition, and thermal evolution. Though small compared to Jupiter or Saturn, these bodies illustrate that size alone does not dictate significance. Even modest worlds record and preserve the history of billions of years of cosmic interaction. The surfaces of dwarf planets often show evidence of past or ongoing geologic activity. Convection in ice, cryovolcanism, and tectonic stresses shape terrain subtly over millions of years. Dark and bright regions indicate compositional differences, while fractures, pits, and ridges record thermal and gravitational stresses. Such features demonstrate that even in distant, cold regions of space, energy persists, quietly reshaping surfaces and maintaining a dynamic planetary character. Moons orbiting dwarf planets add further layers of complexity. Pluto's Charon, for example, dominates the system's dynamics, stabilizing Pluto's rotation and interacting gravitationally to produce tidal effects. Haumea's moons, though smaller, help measure mass distribution and provide insight into collisional history. These interactions illustrate that even minor bodies influence each other, demonstrating gravitational interplay on small scales and reinforcing the concept of interconnectedness throughout the solar system. The orbits of dwarf planets provide rhythm to the outer solar system. Pluto's elongated path, Haumea's rapid spin, Makemake's inclined trajectory, and Eris's distant orbit illustrate the balance between gravitational forces and orbital energy. These motions are slow yet persistent, maintaining stability over billions of years while subtly shaping interactions with neighboring objects. Observing these patterns impart appreciation for the intricate dance that binds distant celestial bodies in their courses around the Sun. Dwarf planets, though remote and faint, are essential to the story of the solar system. They preserve material, structure, and dynamics from an era when planets were forming, colliding, and migrating. By studying them, one gains insight into the processes that produce the inner and outer planets, linking disparate regions through shared origin and evolution. Even in silence and distance, these worlds communicate histories of creation, motion, and subtle interaction. Through continued observation, patterns emerge. Surface features, orbital alignments, and compositional data reveal processes ongoing for billions of years. Bright plains, dark regions, icy deposits, and fractured terrains all speak to energy, collision, and preservation. Each dwarf planet is a chapter in the cosmic story, a quiet record of formation, survival, and change in a system governed by gravity, radiation, and the passage of time. In total, the dwarf planets of the outer solar system remind observers of scale, diversity, and resilience. Though smaller than classical planets, they are complex, dynamic, and historically rich. Studying them provides context for understanding the architecture of planetary systems, the migration and evolution of bodies, and the interplay of composition, energy, and motion. They are distant companions in a vast cosmic neighborhood, quietly orbiting, slowly revealing the narrative of a solar system shaped by billions of years of subtle, persistent forces.
Beyond the distant dwarf planets, the solar system opens into the domain of the gas giants, immense worlds of swirling clouds, powerful storms, and diverse moons. Jupiter, the largest planet, dominates this region with its immense mass and gravity, shaping the orbits of neighboring bodies and maintaining the structure of the outer solar system. Observing Jupiter from a distance, one sees a planet alive with motion. Bands of clouds, turbulent storms, and a palette of browns, reds, and whites shifting in constant silent rhythm. The Great Red Spot, a persistent anticyclonic storm larger than Earth itself, drifts slowly across Jupiter's equatorial region. Winds within the storm reach hundreds of kilometers per hour, circulating energy and momentum across the planet's upper atmosphere. Surrounding cloud bands, composed of ammonia crystals and complex compounds, alternate in color and velocity, producing jet streams and turbulent interactions. Observing these patterns reveals the immense scale of atmospheric dynamics, a natural laboratory of fluid mechanics and energy transfer that continues to evolve over centuries. Jupiter's internal structure contributes to its dynamic exterior. Beneath the cloud tops lies a layer of metallic hydrogen, a state of matter produced under extreme pressure, conducting electricity and generating a powerful magnetic field. This field extends far beyond the planet, influencing charged particles, shaping auroras, and protecting moons from solar wind. The combination of rotation, internal heat, and magnetic interaction creates a constantly changing environment, with visible effects manifesting in cloud patterns, auroral displays, and subtle variations in radiation belts. Orbiting Jupiter are dozens of moons, each with its own character and story. Europa, slightly smaller than Earth's moon, features a smooth, icy surface crisscrossed by dark streaks and fractures. Beneath its frozen crust, a subsurface ocean may persist, kept liquid by tidal heating from Jupiter's gravity. This hidden sea raises the possibility of chemical interactions, energy exchange, and even the potential for life in a place far removed from the sun's warmth. Observing Europa encourages reflection on the diversity of planetary environments and the subtle forces that shape them. Ganymede, the largest moon in the solar system, surpasses even Mercury in diameter. Its surface is a complex mosaic of older, dark regions and younger, lighter terrain, indicative of geological activity and crustal movement. Magnetic interactions between Ganymede and Jupiter reveal both internal structure and charged particle dynamics, adding layers of understanding to the moon's evolution. From orbit, one sees a world of ice, rock, and subtle tectonic processes, quietly preserving a record of billions of years of interaction with its giant host. Callisto, heavily cratered and ancient, offers another perspective. Its surface is a time capsule, bearing scars from countless impacts and remaining largely unaltered by tectonic or volcanic activity. The density of craters, variations in albedo, and subtle topography illustrate the long, slow history of bombardment in the outer solar system. Callisto's quiet surface contrasts with the more active moons, demonstrating the spectrum of activity influenced by proximity to Jupiter, internal heat, and orbital dynamics. Io, closest to Jupiter among the Galilean moons, is a world of fire and motion. Volcanically active, its surface is dotted with hundreds of erupting volcanoes, lava flows, and sulfur deposits. Tidal heating, generated by gravitational interactions with Jupiter and neighboring moons, drives this continuous activity, producing a planet-wide surface renewal. Observing Io is witnessing energy in motion, a dance of forces that shape surface features in real time, contrasting with the slow, quiet evolution of more distant bodies. Saturn, the next gas giant outward, presents a different character, distinguished by its extensive ring system and elegant flattened appearance. The rings, composed of ice and rock particles, vary in size from microns to meters, forming a delicate translucent banded structure. From a distance, the rings shimmer and glint in sunlight, a dynamic display of countless individual particles in orbital harmony. Their patterns, gaps, and divisions reflect gravitational resonances with Saturn's moons and subtle interactions among ring particles, producing a continuously shifting, intricate celestial tapestry. Saturn's atmosphere, primarily hydrogen and helium, exhibits bands and storms less intense than Jupiter, but no less mesmerizing. Storm systems form and dissipate over months or years, moving along latitudinal bands and interacting with wind patterns. Clouds of ammonia crystals float above deeper layers, producing colors and textures that shift with solar illumination and atmospheric currents. Occasional large storms, visible from Earth, demonstrate the latent energy and dynamic equilibrium within Saturn's gaseous envelope. Titan, Saturn's largest moon, is a world with a dense nitrogen-rich atmosphere, ethane-methane lakes, and dynamic weather patterns. Its surface features rivers, dunes, and polar seas, shaped by precipitation, erosion, and seasonal cycles. Observing Titan reveals a planet-like moon with active surface processes, where chemistry, climate, and rotation interact to create an evolving yet quietly stable environment. Titan's haze obscures direct view of the surface in visible light, but radar and infrared observations reveal lakes, channels, and possible cryovolcanic regions, indicating internal energy and material transfer. Other moons, such as Mimas, Tethys, Dione, and Rhea, provide additional diversity. Their heavily cratered surfaces, ridges, and fractures tell stories of impact, stress, and ice dynamics. Each moon responds uniquely to Saturn's gravitational pull, orbital resonances, and past collisional history. Observing these moons collectively emphasizes the complexity of moon systems, the subtle balance of forces, and the interplay between host planet and satellites. Jupiter and Saturn together exemplify the scale and diversity of gas giants. Both are primarily composed of hydrogen and helium, yet differences in internal heat, rotation, and atmospheric dynamics produce distinct visual and energetic signatures. Their moons, ranging from volcanic to icy and geologically quiet, reveal a spectrum of planetary processes on smaller scales. Observing these systems provides insight into formation history, tidal forces, and the ongoing evolution of massive planetary bodies and their satellites. The gravity of these giants influences other bodies in the solar system. Asteroids, dwarf planets, and even comets experience perturbations due to Jupiter and Saturn, shaping orbits, creating resonances, and occasionally directing objects toward the inner solar system. The scale of their influence underscores their role as architects of the solar system structure, guiding the paths of distant bodies through subtle yet persistent gravitational interactions. The visual spectacle of these worlds is accompanied by an intricate ballet of motion. Clouds swirl, rings shimmer, moons orbit in complex patterns, and tidal forces subtly flex surfaces. Observing from a quiet, detached perspective, one appreciates the grandeur without being overwhelmed by scale. The motions are slow yet immense, powerful yet harmonious, offering a sense of calm in the vast, dynamic environment of the outer solar system. Both Jupiter and Saturn are laboratories of physics and chemistry. The interplay of magnetic fields, atmospheric dynamics, and internal heat produce auroras, storms, and subtle variations in emission spectra. Their moons contribute additional energy and material exchange, creating a network of interactions that extend outward into the solar system. Even at great distances, the giant's presence is felt, guiding the motions of countless smaller objects and maintaining a structure that has persisted for billions of years. Exploring these giants emphasizes contrasts. Jupiter's stormy, colorful atmosphere versus Saturn's layered, ringed elegance. Volcanic Io versus icy Enceladus. Dense, geologically variant Ganymede versus cratered, ancient Callisto. Each world contributes to a broader understanding of planetary physics, formation processes, and the diverse outcomes of similar starting materials under different conditions. The moons, in particular, illustrate the balance between internal energy and environmental influence. Tidal heating drives activity in Io and Enceladus, while distant, less perturbed moons preserve ancient surfaces. Atmospheres, where present, interact with radiation, magnetic fields, and particle flows to produce weather, auroras, and chemical cycles. Collectively, these systems demonstrate the quiet yet powerful forces shaping planetary bodies in environments far removed from the warmth of the sun. Observing Jupiter, Saturn, and their satellites is a lesson in scale, motion, and interconnection. The planet's mass, rotation, and internal heat drive atmospheric phenomenon. Moons respond to gravitational and tidal forces. Rings and small bodies interact dynamically. The systems are both complex and ordered, a testament to the balance of forces in a vast, cold region of space. The study of these giants and their moons illuminates formation history as well. Variations in composition, density, and orbital configuration hint at processes occurring during the early solar system: accretion, migration, and resonant interactions. The subtle differences between Jupiter and Saturn and the diversity among their moons preserve clues to the timing, location, and conditions of planetary formation, written across surfaces, atmospheres, and orbital paths. Even the smallest moons contribute to the narrative. Shepherd moons maintain ring structures, while irregular satellites on distant orbits provide records of capture and perturbation events. The cumulative effect of these interactions creates a dynamic, evolving environment where each body, large or small, plays a role in maintaining the architecture and stability of the planetary system. As one drifts through the regions of Jupiter and Saturn, the perspective shifts from isolated bodies to a complex, interconnected network. Gravity, rotation, and tidal forces bind the system, while internal heat, chemical composition, and orbital history shape individual features. Observing in calm, measured detail allows one to appreciate the quiet majesty of these massive worlds and the subtle interactions that define their character. The outer solar system's gas giants, with their moons and rings, embody both power and tranquility. While storms rage, volcanoes erupt, and icy geysers spray into space, the motions are predictable, governed by physics and unchanging laws. The grandeur of scale does not overwhelm, but rather inspires reflection on order, energy, and the persistence of processes over eons.
Beyond Saturn, the solar system continues into the colder, quieter regions occupied by Uranus and Neptune. These ice giants present a contrast to the massive gas giants Jupiter and Saturn, distinguished by composition, atmospheric dynamics, and moon systems. Observing these distant worlds, one senses a serene, measured environment where slower rotation, colder temperatures, and distant solar illumination produce subtle yet remarkable planetary features. Uranus, tilted at an extreme 98 degrees, rotates almost on its side, creating seasons unlike any other planet. Its atmosphere, composed primarily of hydrogen, helium, and methane, exhibits pale blue-green hues due to methane absorption of red light. Cloud formations are faint and diffuse, with occasional bright streaks hinting at localized storms or convective activity. The planet's tilt creates long periods of continuous sunlight or darkness at its poles, influencing atmospheric circulation in ways that remain under study. Uranus's internal heat is modest, contributing less to atmospheric activity compared to its gas giant neighbors. Yet the quiet energy within drives subtle weather patterns and cloud movements. The moon system of Uranus is diverse. Titania and Oberon, the largest, exhibit heavily cratered surfaces, evidence of ancient collisions and minimal tectonic activity. Miranda, smaller but geologically diverse, presents cliffs, valleys, and coronae, features suggesting past internal stress, tectonicism, and possible cryovolcanicism. Ariel and Umbriel display varied terrains, with Ariel showing signs of resurfacing while Umbriel appears darker and older. Observing Uranus's moons reveals contrasts between geological activity and quiet preservation, illustrating the variety of outcomes influenced by size, proximity, and internal energy. Neptune, slightly smaller than Uranus, presents a deep blue hue intensified by methane absorption and unknown atmospheric chromophores. Unlike Uranus, Neptune exhibits dynamic weather, with fast winds reaching over 2,000 kilometers per hour and massive storms that drift across the planet's southern hemisphere. The Great Dark Spot, a storm comparable to Jupiter's red spot, forms, migrates, and dissipates over years, a sign of continuous atmospheric motion. Cloud streaks, composed of methane ice crystals, rise above the deeper layers, producing transient bright features. Observing Neptune provides a window into atmospheric physics under cold, high-pressure conditions far from the sun's warmth. Triton, Neptune's largest moon, dominates the system with a retrograde orbit, indicating capture from the Kuiper Belt. Its surface is a mix of frozen nitrogen, methane, and water ices, with active geysers observed near the South Pole. These plumes, driven by seasonal heating of nitrogen ice, project material hundreds of kilometers above the surface. Triton's geological activity suggests a warm interior, maintained by residual heat and tidal interactions. Its tilted orbit, polar geysers, and smooth plains contrast with crater terrains elsewhere, illustrating the subtle balance of energy and motion in distant satellite systems. Neptune's other moons, such as Nereid and Proteus, show irregular shapes and heavily cratered surfaces, remnants of capture, collision, or ancient disrection events. The diversity among moons emphasizes gravitational interplay, orbital history, and the outcomes of interactions over billions of years. Each satellite, whether geologically active or quiescent, contributes to understanding the complexity of planetary systems far from the Sun. Uranus and Neptune, as ice giants, reveal distinct formation histories compared to Jupiter and Saturn. Higher concentrations of ices, water, ammonia, and methane in solid and liquid forms dominate interior composition, producing unique density profiles and internal dynamics.
Magnetic fields, irregularly tilted and offset from the planetary centers, create unusual interactions with charged particles, generating auroras distinct from those of the gas giants. Observing these fields informs understanding of interior structure and conductive layers, offering subtle clues to planetary formation and evolution.
The moons of Uranus and Neptune also demonstrate varied surface processes. Cryovolcanism, tectonic fractures, and erosion by volatile migration sculpt terrain slowly over millions of years. Seasonal cycles, influenced by axial tilt and distant solar illumination, drive atmospheric and surface phenomena, though at a subdued pace compared to inner solar system worlds. Subtle shading, bright streaks, and albedo variations indicate internal and external forces shaping these distant satellites. Temperature in these regions is extremely low, with Uranus's upper atmosphere around 60 K and Neptune slightly warmer at 72 K due to internal heat flux. Ice compositions remain solid, atmospheric processes are slow, and sunlight is feeble. Despite these conditions, energy persists through tidal heating, radiogenic decay, and gravitational interactions. These quiet forces maintain structural integrity, drive minimal convection, and occasionally produce surface activity, reminding observers that even distant worlds are dynamic on long timescales. The orbital architecture of Uranus and Neptune is stable yet intricate. Each moon maintains a consistent orbit shaped by gravitational equilibrium, while interactions among moons create subtle resonances. Irregular satellites, captured from the Kuiper belt or scattered disk, follow eccentric, inclined paths that illuminate the history of planetary migration and capture events. The balance between stability and perturbation produces a calm yet ever-changing environment, a slow-motion cosmic dance that endures across eons. Observing from afar, the ice giant's subtle rotations and cloud movements reveal energy exchanges between internal layers and atmosphere. Bright cloud streaks, occasional dark spots, and polar features hint at convection and minor storms, a reminder that even in the outermost solar system, planetary processes persist. The quiet beauty lies in slow transformations, contrasting with the more intense dynamics of Jupiter and Saturn, yet equally fascinating in their subtlety and persistence. Triton's capture demonstrates the influence of gravitational encounters on system evolution. Its retrograde orbit, tidal interactions, and geologic activity provide insights into past migration events, energy transfer, and the stability of satellite systems. Other small moons reveal histories of collisional capture, shaping, and survival. Collectively, Uranus and Neptune's moons form a cohesive yet diverse ensemble, reflecting a mixture of ancient formation and dynamic interaction. Magnetospheres of Uranus and Neptune contribute to their uniqueness. Uranus's tilted magnetic field and Neptune's offset field produce asymmetric auroras interacting with the solar wind and charged particles. These phenomena, though subtle at great distance, reveal internal conductive layers and the influence of rotation and composition on magnetic generation. Observing these features adds depth to understanding planetary interiors and interactions with space environments. Icy compositions dominate the moons, producing varied geologic expressions. Cryovolcanic plains, fractured terrains, and impact craters record thermal and collisional histories. Differences among moons emphasize the range of outcomes depending on size, energy sources, and orbital dynamics. Surface textures, reflectivity, and albedo variations provide insights into composition, age, and subtle environmental processes operating quietly over billions of years. The ice giants themselves remind observers of the variety of planetary formation outcomes. Uranus, with minimal internal heat, exhibits faint atmospheric activity, while Neptune, warmer internally, maintains strong winds and dynamic storms. Their satellite systems, shaped by gravity and energy distribution, provide laboratories for studying orbital mechanics, tidal heating, and long-term evolution. Together, they complete the outer gas giant narrative, bridging the solar system from the familiar giants to the distant icy realm of dwarf planets,
Kuiper-Belt objects, and scattered disk bodies. In drifting past Uranus and Neptune, one perceives the quiet majesty of the outer solar system. The pace of change is slow, motions are measured, and energy operates subtly, yet the systems are complex, dynamic, and ordered. Observing these distant giants and their moons illustrates the interplay of mass, composition, rotation, and orbital dynamics that shapes every planetary system. The diversity of moons, the contrast between tilted Uranus and stormy Neptune, and the subtle interactions with distant solar radiation exemplify the range of planetary behaviors. Even in the cold, distant reaches of the solar system, processes continue. Volcanism, convection, cryovolcanism, tidal heating, and orbital evolution, all contributing to the ongoing story of planetary formation and interaction. Collectively, Uranus, Neptune, and their satellites provide a calm yet profound perspective on the outer solar system. Observing them encourages reflection on scale, time, and the persistence of forces that sculpt planets and moons alike. The grandeur is quiet, the activity measured, and the patterns enduring, an invitation to contemplate the distant reaches of our solar neighborhood in gentle observation and deep appreciation.
Beyond the well-charted domains of the gas giants lies a quieter, more dispersed region of the solar system, populated by distant moons, minor satellites, and small celestial bodies. These objects, though smaller and often more remote, hold profound significance for understanding the solar system's structure, dynamics, and history. As we drift through this outer region, the moons of irregular shape and the scattered remnants of planetary formation trace silent, precise orbits, each contributing to the intricate rhythm of our cosmic neighborhood. The moons of the outer planets, particularly those that orbit Jupiter, Saturn, Uranus, and Neptune at great distances, exhibit remarkable diversity. Some are tiny, irregular bodies, captured by gravity long ago, following elongated, eccentric paths that bring them close to the giant planets only at certain points in their orbit. Others are slightly larger, with more regular, stable trajectories, hinting at a past where collisions, capture events, and resonant interactions shaped their current motion. Observing these moons reveals the subtle balance between gravitational forces, orbital energy, and tidal influences, all orchestrating a quiet cosmic dance over billions of years. Many of these outer moons are remnants of ancient collisions. Captured asteroids or Kuiper Belt objects, they bear scars of impact events and collisions that shaped their surfaces and trajectories. Their irregular shapes, heavily cratered exteriors, and sometimes fragmented compositions narrate a history of dynamic processes, forces that molded, shattered, and reshaped them silently, far from the sun's warmth. Each orbit, however slight or eccentric, contributes to the gravitational tapestry of the system, nudging smaller bodies, interacting with rings, and subtly influencing other moons over vast timescales. Saturn's irregular moons, for example, illustrate this diversity. Small satellites, often only tens of kilometers across, circle at high inclinations, tracing orbits tilted significantly relative to the planet's equatorial plane. Their paths reveal capture processes, possibly from the Kuiper Belt or remnants of larger bodies broken apart long ago. Some moons exhibit retrograde motion, orbiting opposite the planet's rotation, evidence of gravitational acquisition rather than co-formation with the planet. Though distant, these moons are part of a complex, interconnected network that responds to perturbations, resonances, and the distant tug of the sun. Jupiter's outer satellites, particularly those beyond Callisto, share similar stories. The Himalaya group and other irregular moons follow wide, inclined orbits, their slow motion a stark contrast to the rapid inner Galilean moons. Their interactions with Jupiter's gravity produce subtle precession, nodal shifts, and long-term orbital evolution. Some moons may eventually collide or be ejected entirely from Jupiter's system, a slow, natural consequence of gravitational balance and chaotic influences over eons. Observing these motions fosters an appreciation for the unseen forces that govern the motions of even the smallest celestial bodies. Uranus and Neptune, though less studied in these outer reaches, also host distant, irregular moons. Many are faint, discovered only through careful observation, and their orbits reflect ancient capture events. These moons offer a window into the solar system's early evolution, preserving information about composition, orbital dynamics, and collisional history. Their long elliptical orbits, coupled with weak solar illumination, create environments where change occurs gradually over millions or billions of years, yet still follows predictable physical laws. Small celestial bodies, such as irregular satellites, trojans, and trans-Neptunian objects, occupy orbits that highlight the interconnected motion of the solar system. Trojan asteroids, for instance, share Jupiter's orbit at Lagrange points, stable regions of gravitational equilibrium where subtle interactions maintain their relative positions. These objects, though minor in mass, reflect the balance of forces that endures across time, demonstrating the quiet order underlying apparent randomness in the outer solar system. Comets, often originating from the scattered disk or Oort cloud, add another dimension to the outer system. Traveling in elongated orbits, some pass near the giant planets, their trajectories altered by gravitational nudges. Icy and volatile-rich comets release gas and dust as they approach the sun, forming tails that point away from solar radiation. These events, transient and ephemeral, connect the outer solar system to the inner, delivering material, energy, and even chemical signatures that inform the story of planetary formation and evolution. The Kuiper Belt, extending beyond Neptune, contains countless small bodies that interact gravitationally with each other and the planets. Objects like Haumea, Makemake, and Eris are accompanied by smaller moons and satellite companions, tracing paths that reveal resonances, captures, and past collisions. The distribution of these bodies preserves a record of planetary migration, hinting at movements of Neptune and other giants that shaped orbital alignments and eccentricities. Observing these minor bodies highlights the scale and subtlety of the forces maintaining solar system stability. Even the tiniest moons, only a few kilometers across, influence and are influenced by their surroundings. Their collective gravity, though minuscule individually, contributes to orbital resonances, ring dynamics, and long-term stability of satellite systems. The interconnectedness of these small bodies illustrates that the solar system functions as an intricate network where even the least massive participants play a role in the larger rhythm of motion and energy exchange.
Collisions among these distant moons and minor bodies, though infrequent, have lasting effects. Fragmentation can create swarms of debris, forming temporary rings, altering orbital parameters, or producing smaller satellites captured by larger bodies. Over millions of years, these processes subtly reshape the architecture of the outer system, demonstrating the long-term evolution driven by energy conservation, gravity, and chance encounters. Observation of distant moons emphasizes the scale of time in the solar system. Their slow orbits, faint surfaces, and minimal activity contrast with the dynamic inner planets and even the gas giants. Yet the patterns they trace, the interactions they undergo, and the subtle perturbations they experience reveal the stability and precision of gravitational physics across vast distances. Each body, regardless of size, contributes to the ordered dance that extends from the sun to the fringes of the solar system. The outer moons and small celestial bodies also connect the story of formation and migration. Their compositions, rocky, icy, or mixed, reflect the primordial materials present during the solar system's birth. Collisional histories and capture events preserve clues about planetary migration, resonances, and the shaping influence of giant planets. In quiet observation,
one can trace the echoes of the solar system's earliest moments across these distant, diminutive worlds. Beyond the giant planets, irregular moons orbit with high inclinations and eccentricities, demonstrating the interplay between stability and chaos. Some moons are stable over billions of years, while others slowly spiral outward or inward due to tidal forces, perturbations, and resonances. These subtle motions, largely imperceptible in human timescales, illustrate the continuous interconnected motion governing celestial mechanics. Small bodies such as centaurs orbiting between Jupiter and Neptune bridge the inner and outer regions of the solar system. Their orbits evolve over time due to planetary interactions, sometimes sending them toward the inner solar system as short-period comets. These travelers carry with them frozen remnants of the early solar system, revealing chemical and isotopic compositions that illuminate the conditions of planetary formation far from the Sun. Through observation of these outer moons and minor bodies, the solar system appears as a cohesive, interconnected network of bodies, each orbiting in silent harmony. Gas giants, their moons, dwarf planets, and minor satellites all contribute to a balanced system. Forces act over immense distances, yet result in coherent, enduring patterns. Observing these quiet motions inspires awe at the stability, scale, and beauty of the cosmos. The study of these distant objects also demonstrates the scale and diversity of the solar system. Sizes range from tiny fragments only a few kilometers across to dwarf moons hundreds of kilometers wide. Compositions vary from pure ice to rocky, metallic, or mixed bodies. Orbits range from circular and regular to eccentric and inclined, reflecting past collisions, captures, and the influence of distant giant planets. This diversity enriches our understanding of planetary system evolution, dynamics, and architecture. Even in their quiet existence, outer moons and small bodies remind observers of the solar system's interconnection. Their orbits influence one another, affect ring structures, and sometimes send material inward to interact with larger planets. They participate in the gravitational rhythm that maintains order across millions of kilometers, a subtle network of motion that connects the inner planets, gas giants, and distant dwarf worlds into a coherent, flowing system. Observing these objects cultivates appreciation for long-term processes. Slow rotations, gradual orbital evolution, and minor surface changes unfold over millennia, imperceptible in daily life, but critical to planetary history. These remote moons and minor bodies preserve ancient records of impacts, collisions, and gravitational interactions, offering insights into the broader narrative of solar system formation and evolution. The interconnected motion of these distant moons and small bodies highlights the elegance of orbital mechanics. Even the tiniest satellites, through resonance, perturbation, or collision, contribute to a harmonious structure. Their paths, dictated by gravity and inertia, form a quiet choreography, demonstrating how vast numbers of individual elements interact to create the overall order of the outer solar system. As we drift among these remote worlds, one notices the subtle variations in color, brightness, and composition. Ice, rock, and mixed materials catch the faint sunlight differently, producing contrasts that mark past collisions or compositional differences. Shadows and light on cratered surfaces reveal texture and depth, while faint trails of dust or faint rings hint at ongoing processes, no matter how slow or distant. The study of these outer moons and small bodies also informs understanding of potential future exploration. Spacecraft navigating these regions must account for irregular orbits, gravitational interactions, and potential collisions. Their subtle dynamics teach lessons in navigation, long-term trajectory prediction, and the interconnected nature of celestial mechanics, providing practical knowledge alongside scientific insight. From the perspective of an observer floating beyond the main planets, the solar system appears as a vast interconnected web of bodies, each orbiting in silent harmony. Gas giants, their moons, dwarf planets, and minor satellites all contribute to a balanced system. Forces act over immense distances, yet result in coherent, enduring patterns. Observing these quiet motions inspires awe at the stability, scale, and beauty of the cosmos.
As we move beyond the outer moons and small celestial bodies, the solar system as a whole unfolds as a vast interconnected network, a delicate orchestration of matter, energy, and motion. Each planet, moon, asteroid, and minor body participates in a silent ballet, tracing paths dictated by gravity, inertia, and the residual energy of the solar system's formation. Observing this interconnected system reveals patterns both subtle and profound, a testament to the quiet laws that govern celestial mechanics. The motion of planets and moons demonstrates a balance between stability and change. Orbits, while largely predictable, are subtly influenced by gravitational tugs, resonances, and tidal interactions. Even distant moons, far from the sun's warmth, affect one another over millions of years, nudging orbits and influencing rotations. Asteroids in the asteroid belt maintain positions that avoid collisions with resonance with Jupiter, illustrating how chaos and order coexist in a cosmic dance. Understanding these interactions highlights the solar system as a cohesive, dynamic entity rather than a collection of isolated bodies. The solar system's interconnected motion also provides perspective on scale and time. Distances span millions to billions of kilometers, yet forces propagate consistently across this immense space. Movements that appear slow on human timescales reveal patterns of stability and change when viewed across millennia. Moons orbit, rings ripple, comets swing inward and outward, and planets drift imperceptibly in response to gravitational interactions. These motions remind us that time in the cosmos flows differently, emphasizing endurance, patience, and subtlety in the unfolding story of matter and energy. As we drift farther from the sun, the sense of unity among celestial bodies becomes clear. Gas giants shepherd asteroids, moons influence rings, and minor satellites trace paths in delicate gravitational balance. Even comets from the Kuiper Belt or Oort cloud are part of the larger system, their eccentric paths linked to the planet's positions in past migrations. The solar system is not static. It is alive with measured, persistent motion, an immense, elegant choreography that has endured for billions of years. Observing this quiet motion encourages reflection on humanity's place in the cosmos. From our vantage point on Earth, we experience time and space differently, yet the same forces govern our planet as they govern the most distant moons and asteroids. The cycles of seasons, tides, and orbital periods are echoes of the larger universal patterns. By considering these connections, we gain perspective on the resilience, balance, and beauty of the cosmic order, appreciating our world as part of a vast interconnected system. The distant moons, minor bodies, and subtle interactions collectively preserve the history of the solar system. Collisions, captures, and migrations are recorded in orbital paths, surface features, and composition. Each crater, fracture, or orbital eccentricity tells a story of events occurring billions of years ago, a slow-motion archive of cosmic history. Observing these remnants provides insight into planetary formation, migration, and evolution, revealing a complex narrative written in ice, rock, and orbital mechanics. Even the smallest bodies contribute to this narrative. Tiny moons maintain resonances that stabilize ring structures, or perturb larger satellites. Asteroids and comets deliver materials and energy across vast distances, connecting distant regions of the solar system. Each movement, though imperceptible in a human lifetime, is integral to the overall harmony of the system. The interconnectedness is a quiet reminder of cause and effect at a cosmic scale, where even the seemingly insignificant shapes the whole. The beauty of the outer solar system lies in its contrasts. Giant planets dominate with mass and energy, yet their distant moons maintain gentle orbits shaped by subtle forces. Rings shimmer in delicate bands, while icy satellites harbor quiet geological activity. Farther still, minor moons drift in regular or eccentric paths, illustrating stability amid isolation. This interplay of magnitude and subtlety, motion and stillness, chaos and order, creates a tapestry of complexity and elegance. Contemplating the solar system as an interconnected whole encourages a perspective of patience and humility. The motions we observe are persistent and enduring, guided by fundamental forces that have acted since the system's formation. Even as human lifespans and civilizations are fleeting, these patterns persist, offering lessons in endurance, balance, and interconnectedness. Observing planets, moons, and minor bodies in calm, measured reflection reveals the intricate choreography of the universe. From Mercury's scorched surface to Neptune's icy storms, every planet, every moon, and every minor body participates in a subtle conversation of motion and energy. Orbits resonate, tidal forces shape surfaces, and collisions leave lasting imprints. The interwoven paths of celestial objects remind us that the solar system functions as a network where no body exists in isolation. Gravity, inertia, and time together produce a stable yet dynamic structure, a system both ancient and ever-changing. The distant objects beyond Neptune, from irregular moons to Kuiper Belt bodies, further extend this interconnected web. Their orbits, influenced by Neptune's gravity and past interactions with the giants, trace long-term stability, punctuated by occasional perturbations. These remote members illustrate the reach of gravitational influence and the delicate balance maintained across billions of kilometers. Even in isolation, each object contributes to the rhythm and structure of the solar system. Observing the solar system as a whole encourages reflection on the broader universe. Our planetary neighborhood is just one system among billions in the galaxy, yet it demonstrates principles that govern celestial motion universally. The quiet, interconnected dance of planets, moons, and small bodies is a microcosm of cosmic order, illustrating that even in apparent stillness, processes are ongoing, interactions persistent, and patterns enduring. Through patient observation, the solar system reveals the elegance of balance. Each orbit, rotation, and interaction is part of a vast mechanism operating on timescales far beyond human perception. Tides, resonances, and collisions shape environments. Motion conveys energy across space. Matter preserves history. This quiet order inspires contemplation, encouraging an appreciation of cosmic time, scale, and the interdependence of celestial bodies. As we conclude this journey, the solar system appears as a living, breathing entity, each body contributing to a harmonious structure. The sun's gravity anchors planets, moons orbit faithfully,
rings shimmer, and minor bodies drift in silent synchrony. The distant reaches, though cold and faintly illuminated, are alive with measured motion, a testament to the persistence and precision of universal laws. Observing these motions fosters a sense of calm, perspective, and connection to a larger cosmic story. In reflecting on the solar system's interconnected nature, we recognize that our understanding of planets, moons, and minor bodies is both scientific and poetic. The patterns, forces, and histories we observe are grounded in physics, yet they invite wonder and contemplation. Each orbit, storm, and subtle interaction becomes a quiet story of persistence, harmony, and the beauty of the cosmos. Thank you for drifting through the solar system and exploring its planets, moons, and small celestial bodies. If you enjoyed this calm journey through our cosmic neighborhood, please like, subscribe, and leave a comment sharing your favorite planet or moon. Your engagement helps continue these explorations and inspires further journeys into the wonders of the universe.